This video is about rotational kinematics mostly, but we're going to be covering kind of rotation, like an intro to rotation. Um, and so we'll be covering, yeah, rotational kinematics, conversions of units. We're going to relate rotational and translational quantities, and we'll talk about constant rotational motion. So an object that's rotating, um, oh, I don't know, uniformly. It's not speeding up or slowing down its rotation. So just to start off with what rotational motion is, versus translational motion. So in the old days, which was, the days leading up to today, we just talk about a ball and maybe it has some velocity v. And so it's going to move from here and eventually maybe it will, eventually it will be right here. So it's moved from here to here. We say it has translational motion because it changes its position, in a linear way. Rotational motion would be it's kind of like spinning. So here I have be like a baton, and this thing will spin about this axis. Maybe it goes, this way. And so this would be rotational motion. In class, we just took a bar and we just, yeah, kind of spun it around. Um, an object can have both of these. It can have translational motion and it could be spinning. So through a picture of Obi-Wan Kenobi, uh, if you've seen Star Wars, the prequels, and yeah, sometimes he'll twirl his lightsaber, and so this thing, the lightsaber will have rotational motion about an axis right here where he's holding it, and this lightsaber will go around, it'll spin. Sometimes Obi-Wan Kenobi is running, and if he does both of them, he's twirling the lightsaber and he's also running, then yeah, the lightsaber will have rotational motion, but it'll also be translating, so it can do both. Sometimes the rotational motion is related to the translation. So, for instance, a ball rolling on a table, it's going this way. And as it moves, of course, the ball is rotating, Maybe that's not a great drawing, but it's spinning as it rolls. And so sometimes the rotational motion is related to the translational motion. The faster the translational motion, the ball is rolling down here faster, it is rotating faster. Or if it's going slowly, it's rotating slowly. Because, of course, the ball is in contact with the ground. For something like the lightsaber, Obi-Wan can be twirling it really fast and walking slowly, or he can be twirling it kind of slowly and walk, and vice versa. I've already forgotten what I've said, but in that case, the rotation has nothing to do with the translational motion. Okay, cool. So I think that covers those types of motion. So yeah, let's come here to this picture first and move it over here. Let's suppose this, I don't know, let's say it's a disk or something, starts rotating. And let's say it starts rotating counterclockwise. Let's say. Well, let's say it only rotates slightly. So at first, maybe there was we just draw a line from the center to here. We kind of say that's like the initial position of the disk. And as it rotates, I don't know, sometime later, maybe that same line would now be here. So it's like rotated and spun around. And so now it's here. You can think of a spoke on a wheel or something. Well, we'll call the initial position um, of where it started, we'll call that theta. And I'm sorry, theta naught. And the final position or the position later in time, we'll call that theta. And so let's write this down. Let me rewrite these. This is theta naught, and this is theta. I didn't like how those came out. Okay, so the initial angular position and the final angular position, or the position later in time. So right away we have this term angular. This just means rotational. And we'll kind of have to get used to that. It could say angular position. It could say how many rotations, okay? That sort of thing. And the units for the position is in radians. You might think, um, turn it this way. Let me turn it so it's like this. And you might be familiar with degrees, like this would be like 0 degrees. Oh, that's like real thick. 0 degrees. And over here would be, oh, I don't know, this is 180, maybe this is like 170 degrees. Okay, so degrees is one way we use to show angle, one way to measure angle, but we don't do that with rotational kinematics. We use radians, and so let's just get familiar with the radians. And of course, that doesn't erase. There we go. So again, if this is 0, which oftentimes we'll start it at just 0 radians, it's just like a starting point. And 1 radian is about it's about right here. So like if you drew a line to about right there. What a radian is you take the radius and you stretch it over the surface of that circle. Okay, so that this is one radius length. Okay, the angle here that it's making is 1 radian. And if you do that, so this is about 2, 3 is a little bit less than 180 degrees. And if you do this long enough, you end up with something like this. It's about 6.28, or in other words, a full rotation around this circle here is 2 pi radians. Hopefully you're familiar with that, but if you're not, well, there's your introduction. So in other words, 360 degrees is like equivalent to 2 pi radians, which it just means 6.28. You can, and it's related to pi, so these decimals continue, but it's about 6.28 times the length of the radius to go around the full circle. Cool. So we have the first two, the initial angular position, final angular position in radians. Well, when something's rotating, it can have a rotational speed. So just gonna clear these up real quick. Well, I haven't given up yet. So let's see here. Don't need to do that, but just for clarity. So here's the center. And let's just say this is our starting position here. And this thing starts rotating. And in fact, let's say it's like a bicycle wheel, and you're starting from rest and you're starting to go faster and faster. And as this goes around, we can say that this has an angular speed or a rotational speed. And the letter we use for that is a Greek letter called omega. So right away, I'm going to say this is not W, so don't write that. Or it's not capital W. This is omega, which means angular speed, or it goes by many names. Angular speed, angular velocity, rotational speed, rotational velocity. and it's how many radians per second it's turning. So, if this was 1 radian per second, and I'm just kind of guessing here where 1 radian would be, it's about that much. It'd go from here to here, it would spin that much from here to here in 1 second. Or if it was 2 radians, well, 2 radians would be about, somewhere here in 1 second. Anyway, that's angular speed. So my example, the initial angular speed was 0, but it's not always 0. It could start at some initial rotational speed. And so we have to get used to that. This is rotational velocity, but you might see angular velocity, or you might see angular or rotational speed. And they all mean the same thing. This is omega naught for the initial, and some angular speed later in time would just be omega. And the units are radians per second for both of those, of course. So, for that matter, if the angular speed is changing, which they will in these problems, then we have a rotational acceleration. This is Greek letter alpha, so it's just a fish. It's just like a fish symbol. I never like how I'm writing these. There we go. And we call that the rotational acceleration. Oh, you can also call it angular acceleration. So I'm used to angular, and so kind of drives me a little bit nuts trying to say rotational. But anyway, rotational acceleration, which of course are in radians per second squared. And t, of course, is time. Now, these look really familiar. They should, at least the way we've written them here. It's because this is kinematics and we've done this before. So here are the relationships, and you will certainly recognize the pattern here. Omega equals omega naught plus angular acceleration times time. Theta equals theta naught plus initial angular velocity times time plus 1/2 angular acceleration times time squared. Angular speed, final angular speed equals initial angular speed plus 2 angular acceleration times theta minus theta naught in parentheses. Of course, these are our kinematics equations for rotation. And all of these only work when your angular acceleration alpha is constant. And so if it's not constant, you can't use these, or at least they don't can't use them and get a correct answer. Is there something else I was going to say? I think I've covered it. Hopefully I did. Otherwise, we'll come back and we'll talk about this. Cool. Let's do an example. So a disk initially rotating at 12 radians per second slows to a stop in 5 seconds at, constant angular acceleration. So here's a picture of the disk, drawing it from the side, and they're showing the direction of the spin. Yeah, so question A is what is the angular acceleration? And before we answer that, in fact, let's make a list. We're going to figure out angular acceleration and then through what angle does it rotate. So we know 5 seconds We know the initial rotating speed is 12 radians per second. I had a really good question in class. Do you have to write RAD over S? Yes, you do. Don't do this. Yeah, don't do that. And yeah, so that was a good question. And of course, it comes to a stop. It's another number. The final angular speed is 0. Cool. And just like in oh kinematics, when an object was moving horizontally, we often make that starting position 0. And so here we'll also make that initial rotational position 0. Cool. And we'll look for alpha. Typically, to solve the kinematics equations, you need 4 out of these 6 numbers. And of course, these last 4 work with equation number 1. So again, I'll say do not write W. This is not W. It's got to be omega. Okay, which by the way, we also call, this is funny. This is Pokeball not. This is Pokeball. This is baby butt not. This is baby butt. This is fish, and that's T. And so we will start calculating. We'll do our substitution. And so this is negative 12 over 5, which is negative oh, 2.4. Yeah, radians per second squared is alpha. So if it is spinning this way, the angular acceleration is simply in the opposite direction. That's what the negative means, just opposite direction. Which in kinematics, the negative has always meant the opposite direction. Just sometimes we say it was to the right, so we would say left. Up, so we would say down, or, so on. Okay, so we have angular acceleration. Through what angle does it rotate? Well, of course, we're trying to solve for theta. Use any equation you want. I'm going to use this one. That's 0. That is not 0. This is 12 and 5 and 1/2 negative 2.45 squared. I don't remember that number, but it's been several days. Okay, that's it. And the units for that is radians. So it has rotated 30 radians. If a full complete revolution or a full complete rotation is 2 pi radians, what we can do is simple, real quick, like a rough calculation. 2 pi radians is about 6.28. And so if you just take 30 radians divided by 6.28, we would know about how many rotations it's done, approximately. And so it comes out to like 4.77, really close to almost 5 rotations, to give you an idea. Okay. So as this thing is slowing down its spin, it comes really close to having been gone around, 1, 2, 3, 4, almost 5 when it stops. Cool. Let's keep going. At the beginning of the video, I said we do conversions, talking about conversions. We need to be able to convert from radians to rotations, which is, of course, this variable position. Kind of like what we just did right now. So we had 30 radians. We want to know exactly how many rotations. We kind of did it. We're going to show you how to do it, properly. And we also want to go from, uh, angular speed, radians per second to RPMs, which, by the way, is rotations per minute. And this is how I will write it, rotations per minute, or RPM. And back and forth. So what if we go here, then we go there? So we have to memorize two things. One of these is really easy to memorize. One rotation is 2 pi radians, and then one even easier to memorize is 1 minute is 60 seconds. Okay, so let's come over here to example one. Example one, so we have an angle of 22 radians, and we want to convert how many rotations is this? So here's what we do. We write theta equals 22 radians, and we are going to multiply by a conversion factor. And conversion factors have a value of 1, so it's kind of like saying 22 times 1. It's not going to change our answer, in other words. Our answer will still be correct. And so we have to remember the conversion between radians and rotations. And once we do that, here's what we're going to do. We notice that there's radians. This is kind of on top of the fraction, and we want to get rid of radians. So over here is going to go the conversion factor. We need to put radians in either the top or the bottom. But if we want to get rid of radians, this really has to go in the bottom. We don't want to put it at the top because that would be radians squared, which is not what we want. We want radians and we want two rotations. So always start putting the units first because we want to make sure radians goes on bottom. Sometimes radians will go on top and rotations will go on bottom. Okay, so it all depends on which way you're trying to convert. And then we remember our conversion factor. It's one rotation for 2 pi radians. 22 times 1 divided by 2 pi, or just 22 divided by 2 pi. This is one of the times where I do want you to try this on your own. Try doing 22 divided by 2 pi and make sure you get the right answer. You will either get 34.5 or 34.6 really, or you would get 3.5. What is the correct answer? Correct answer is 3.5 rotations. Kind of rounding 3.50 rotations. And so if you got the other answer, well, here's what's happening. You type this in the calculator, 22 over 2 pi, and it will give you the 30, I don't know, what did I say? 34.6. It'll give you that. Or if you do 22 over in parentheses 2 pi, close parentheses, then that will give you the correct answer, which is 3.5. Your calculator will see this and think, okay, this is what they want. Your calculator will also see this and do this, which is 11 times pi, which is 30. Yeah, it's not the right answer. So you have to make sure when you use pi to put parentheses on it. Of course, this is all a moot point if you just use a fraction on your calculator. Let's do one more. Omega is 78. Let's write rotations per minute. This will help us convert it. We want to convert it to radians per second, but we need to get rid of two units. We need to get rid of rotations and we need to get rid of minutes. So make two conversion factors. And myself, I don't even know how I just kind of do whichever one I want first. Maybe let's get rid of rotations first. And so right here in this first conversion factor, we need to put rotations on the bottom, and we are converting rotations to radians. So we'll put radians up here, and we remember our conversion now. We put in the numbers. One rotation is 2 pi radians. Well, that's good. That'll get rid of rotations. Now we need to get rid of minutes. Minutes is on the bottom of these fractions, right? Or on the bottom of the fraction. So to get rid of it, we need minutes on top of the fraction as well over here. So there's minutes, and we are converting that to seconds. And now we put in the numbers. And, um, it's good advice to always start with the units first before you put in numbers. Don't put in numbers first and then put in units. It should be the units first. Um, because if I'm putting in numbers, I'll say, oh, I'll just do 60 seconds for 1 minute, and this is wrong. Hopefully that's obvious to you. And 1 minute is 60 seconds. It's an S. Cool. And I always double check. So do I have something on the top and the bottom? I do. I can get rid of those. Do I have this on the top and the bottom? I do. And I'm left with radians and left with seconds. So this would be 78 times 2 pi, all divided by 60. 8.17 radians per second. Looks good to me. Okay, conversions, that's good. We'll typically have a problem like this, though, where it's kinematics and we have to convert. So we'll do another example. A windmill initially at rest. So that's zero, but which zero? Is it this one or is it this one? So it's initially at rest means it's initially not rotating. So its angular speed or rotational speed is zero. And it starts rotating with an acceleration, rotational acceleration of 40.45 radians per second squared. And so they want to know what is omega in RPM at t equals 8 seconds. Well, they gave us another number. And this one, we just make zero at its starting position. And so let's find omega. I think the first equation is perfect for this. For this job, we'll put zero here. This is 0.45 times 8. So baby butt equals 3.6 radians per second. But they want it in RPM. Not a problem. We'll put our conversion factor and run out of space. Just have to squeeze this in here. Let me get rid of radians. So if I'm getting rid of radians, it needs to be on the bottom of one of these fractions. We are converting that to rotations. One rotation is 2 pi radians. We need to get rid of seconds because, we're trying to get to minutes here. If I have one on the bottom, I need to have one on the top. And we'll put minutes here. 1 minute is 60 seconds. Radians does cancel, seconds does cancel. So I will be left with rotations per minute, which is what I want. That's 3.6 times 60. And divide by parentheses 2 pi, close parentheses. Sorry, 34.4 rotations per minute, and I'm just going to write it now as RPM. Yeah, good enough. It's good to note, even though they wanted it in RPM, if we ever use that number again, we need to use the radians per second, as we initially wrote at the start of this video. So this is still at 3.6 radians per second. But it's kind of a moot point because, well, it's not a moot point, but don't really need it for this one. We want to know how many rotations does it go through in 8 seconds. Well, that's actually an important point to make. I forgot my numbers. Okay, so this is 0. This one is, this whole term here is 0, so theta equals 1/2 0.45 times 8 squared. (14.4 radians). But they want it in rotations. So how many rotations was 14.4 radians? We'll have our conversion factor. Radians is on the bottom. Rotations is on the top. One rotation is 2 pi radians. The radians will cancel. So this is 14.4 divided by 2 pi. Mhm. It's about 2.3 rotations. Yeah, 2.3 rotations. Cool. So what else were we going to cover today? We just did rotational kinematics intro, and then we did conversions. Let's talk about relating translational quantities. Okay, so here's our example. It's a turntable, and there's a coin, which is this dot right here, sitting on the turntable, and the coin is a distance away from the axis of rotation. Which I'm just going to write as a dotted line here. So the coin is that far away from the center of rotation, and it's rotating. Angular speed omega, which I'll also show over here. This is a top view. It's got, oops, it's got angular speed omega, so it is rotating around here. And okay, it's got angular speed. The coin, as it's spinning this way at this particular moment, this coin has a linear velocity or a linear speed, which we will call v, which we know, we've done this before actually, but we have an equation that will relate these quantities together. So v equals r omega. Let's write this out. So V, we can call this translational speed, or we can call this speed. We can just say it is like if we in a question we ask how fast is it moving, we're talking about V. If we say what's the speed of the object, we're talking about V. If I say what is angular speed, well, that's omega. But if it's any of these, and maybe also, yeah, linear speed. What is the linear speed? I'll refer to V. R is the distance from the axis of rotation to a point of interest. And sure, oftentimes it might be on the rim, but in this case, this coin is, some distance here, which is not the radius of that circle. So we'll call it R and not capital R. We use capital R for the radius of things. Cool. And then omega, of course, is the angular speed or angular velocity, rotational speed or rotational velocity. This is in units of meters per second. This is meters, and this is radians per second, as we already discussed. Cool. All right. Um, it's kind of an aside here. Oh, no, not an aside. It's also important. So let's say it's going constant omega, constant angular speed. That's just a turntable playing a record or something. There's a coin on there, but forget about that. It's just rotating at constant speed. It's not speeding up its rotation. It's not slowing down its rotation. And we're placing the coin there. Does the coin have any, is the coin accelerating? And you might think yes, you might think no. You might think no because its angular acceleration is zero if it's not speeding up its rotation or slowing down its rotation. But there's other types of acceleration. And in fact, there is a centripetal acceleration, right? It's undergoing circular motion, so it has a centripetal acceleration. Centripetal acceleration, we actually already know the equation for this. This is v squared over r. So if you know this v, you've calculated this v, and you know the distance to it, then you can calculate it that way. But we can also do this. V is r omega, so I'm kind of substituting it here, which is r squared omega squared over r. And so another version of this equation is r omega squared because it cancels. So you don't need those, but we do need these. And you know what? These are important, so I'm gonna box these in. Okay, we already knew that one, but we know this one too, which of course, this is centripetal. It's acceleration that changes not v or theta, it's changing the direction of that object. And then finally, Let's say it's not going at constant omega. By the way, you can still calculate centripetal acceleration if its rotation is changing, increasing or decreasing. Let's say there is, you know, angular acceleration here. Well, so it's in other words, the turntable is going faster and faster and faster and faster. The rotation rate is increasing. Well, it also has a tangential acceleration. In other words, now its linear speed will be changing, and controlling that is the tangential acceleration, which is in meters per second squared. And of course, I've forgotten, but we need uh, an equation. I think that's what I was originally trying to write, which is r, the distance from the axis of rotation, times the angular acceleration. So we have some formulas. Let's do two real quick examples here. Suppose the coin is 0.12 meters from the center, and the turntable accelerates from rest to 5 radians per second in 4 seconds. Let's determine all of these quantities here. So we'll start writing these down. Okay. Um, accelerates from rest to 5 radians per second in 4 seconds. Let's make that 0. And so we want we want to know what is alpha. So let's use equation 1. This is 5. And sorry, I'm gonna try to speed this up a little bit. We've done the kinematics already, so this is 5 over 4, which is 1.25 radians per second squared. B is, okay, what is theta? I choose equation 2, whoops, not A, alpha. Oh, we can get rid of these terms. 1 half 1.25 times 4 squared. And radians. Okay, it doesn't say, rotations or anything. So, okay, part C. Now we need V. What is the speed of the coin at 4 seconds? That's V is equal to R, which is 0.12 is the distance, and omega is 5 radians. What is that, 0.6? 0.6 meters per second is its linear speed. Okay. And then D, centripetal acceleration. Let's use the new one. And so this is 0.12 times 5 squared, which, yeah, of course, 0.6 times 5 is 3 meters per second squared is the centripetal acceleration. Yeah, good enough. Cool. And then the tangential acceleration is r alpha. It's 0.12 times 1.25. 0.15 meters per second squared. There we go. All right, let's keep going. Okay, so let me explain this picture here. We have a rigid surface here. We have two cables or two beams um, holding a rod, okay, at one point. And let's just say I'm holding it for right now. And, once I let go, what's going to happen is this rod is going to start to rotate about this pivot point here, and it'll swing this way and something like that. But what we're thinking of is what is happening at this moment that we let go. There will be an angular acceleration of 6 radians per second squared once we let it go. The rod has a length, and when we use length, let's use a curvy little L here of 2.5 meters. Let's get rid of that. Okay, so there's the end of the rod, and then there's the middle of the rod, which is B and then A. We want to know what is the acceleration of point A and what is the acceleration of point B. And we're not asking about angular acceleration because we already know what that is. What we want to know is the tangential acceleration. In other words, at the moment of release, what is AT here, which I'm actually going to call A of A, and over here, what is the tangential acceleration here, which I will call B. And so the equation is, or this version, let's do for A first, I think it said. The tangential acceleration at point A is r alpha. But what is r? Since we're going to have two different distances here, let's call this RA times alpha. Well, you can do that in your head, but for a moment here, let's substitute R alpha, I'm sorry, RA, let's say is half the length of the rod, so that's L over 2 times alpha. And now let's substitute some numbers. That's 2.5 over 2 times 6. So I get tangential acceleration of point A to be 7.5 meters per second squared. I don't know why I did that in color. Let's do the tangential acceleration of point B will be the distance to B times alpha. The distance to B is the length, which is 2.5 times 6, which is, I don't know, 15. And there it is. Okay, last thing. So we can end this video. There's no reason why this one came last. This is just the last one. It's a constant rotational speed. So in other words, what if omega is constant? In other words, There is no angular acceleration. Well, this looks real familiar to us. You might recall this one. And so, yeah, substituting the necessary equations, we get omega is equal to 2 pi over t, which is the period. It's the time for one rotation. So omega equals 2 pi over t. Now let's just jump right into an example. What is the rotational speed of the Earth on its axis? Well, rotational speed is, well, the Earth on its axis. Okay, so the Earth on its axis, the Earth is spinning, but its spinning is not increasing. Its spinning is not slowing down. At least, let's be practical. It's not. So this is 2 pi over t. What is the period? In other words, what is the time it takes for one rotation of the Earth? Some people will say 365 days, which is wrong. And some people will say 1 day, which is right, but we can't just put one here. Remember when we do these, oh, I have it right here. This is in seconds. So in other words, it takes 1 day, but how many seconds is in 1 day? Well, 1 day is 24 hours. Each hour is 60 minutes, and each minute is 60 seconds. So it's 24 times 60 times 60, which I didn't want to guess incorrectly here. It comes out to 86,400 seconds. And so this would be 2 pi over 86400. Oh, what a wonderful number. And this is 7.27 times 10. Let's count decimal places for 5. This is negative 5 radians per second. Kind of a slow rotation, it seems. But let's take this one step further. So here's the Earth, and let's say it's spinning about its axis, which it is, which is actually on a tilt. So I kind of drew it kind of nicely there. Um, and let's say it's spinning this way because it is. If this is the North Pole, it is spinning that way. Um, yeah. What is the speed, tangential speed, of somebody on the equator? So in other words, what is v, which is r omega? Well, that means we need to know the distance from the center of the Earth. In other words, the radius of the Earth, which I actually don't remember. Let's just call it 6.4 times 10 to the 6 meters. Oops. Times omega, okay, which is 7.27 e negative 5. Oh, sorry, I use that e notation in astronomy a lot. This is times 10 to the negative 5. Yeah, it's about 465. Okay, let's just round it meters per second of speed. So that's how fast somebody's going. The tangential speed. Cool. That about does it for this video.